Alright, welcome back to part 2. We're going to do a couple of examples now that include the moment of inertia and show you how to apply Newton's second law of rotational motion. Okay, so the example that we're going to go through is example 10 in your book on page 261. So if you get lost or you'd like to follow along with that, that's what we're doing. And the example presents us with an electric motor that's needing to spin a blade from rest to an angular velocity of 80 revolutions per second in 240 revolutions. The blade has a given moment of inertia, and we want to figure out what net torque would need to be applied for this to happen. So the analog of this is we've got something, if we were thinking about linear kinematics, we've got something starting from rest, reaching a final velocity after a certain displacement, and we want to find the force required to do so. That would be the linear analog. In this case, we have an initial angular velocity of 0. And our angular velocity will need to be in radians per second. So they've given us some of the information in a form that we can't use. The final angular velocity, they told us, is equal to 80 revolutions per second. And we're going to need to convert that into radians per second. We can do that by remembering that each one revolution is 2 pi radians, and we can do the conversion. So I'm going to get my calculator real fast. So we've got our calculator. So we've got 80 revolutions per second times the number of radians per revolution, 2 pi. And that'll give us that our final angular velocity is 160 pi radians per second. And we can round that if we want, or we can leave it the same. So we'll just leave it like that. The next thing they told us was that this happened in 240 revolutions. That's our change in angular displacement. 240 revolutions. Again, we're going to need to convert that to radians, and we'll do it in the same way with our calculator. And so this is going to end up being 480 pi radians. And they gave us another bit of information, which was that the moment of inertia of the blade is 1.41 times 10 to the negative third kilograms meters squared. And you can see those units match up with the equations for the moments of inertia we were looking at in video 1. So that's all of our information. Now we need to look at the equations that will help us solve this problem. We have a blade that looks like this, and the blade has some torque acting on it. Let's say that it's being pushed in this direction across some radius r, and that's our torque. And the blade is rotating with some angular frequency or angular velocity, that's changing based on the torque that's being applied. And we want to calculate the torque that would be necessary. So one equation is that the net torque is equal to the the moment of inertia times the angular acceleration. We also need to find the angular acceleration. We have an equation for the angular acceleration that came from an analog in linear kinematics that was the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the change in angular displacement. We can solve that equation for angular acceleration. We know that the initial was 0, and so we have the angular velocity divided by 2 times the change in angular displacement is equal to the angular acceleration. And we can plug that into our equation up here, and we'll get that the net torque, which is what they asked for, is equal to the moment of inertia times the square of the final angular velocity divided by 2 times the change in angular displacement. And we can go ahead and plug that into our calculator. So we're going to get our moment of inertia, 1.41 times 10 to the negative third times 160 pi the quantity squared. That's our final angular velocity, all divided by 2 times our angular displacement, which was 480 pi. And there we go. And so the units in this case are the units of torque, Newton meters. And so that's how we'd take care of that problem. Let's do one more problem that's a little bit more complicated to understand conceptually. This problem is example 12 from your book. And basically, we have a pulley that has 2 different axes. So in the book, they draw it like this. We have an inner axis that has a pulley cord coming off of it and a crate that's hanging off of that inner axis. And then we have an outer axis. Didn't draw that very well, but that's that. And we have another pulley cord coming off of that that a motor is pulling on. So there's a force being exerted to pull and rotate this system counterclockwise. All right. If we were to draw this in perspective, maybe it would make it easier to see what they're talking about. We have an inner axis here, and then we have an outer axis here, like this. So the first cord is wrapped around like that and coming down, and the second cord is wrapped around this outer axis, going out like that. Okay. So they gave us some information. They tell us that the crate has a mass of 451 kilograms. They tell us that the 2 cables don't slip, which is important for us so that we can make an assumption later. They tell us that the inner radius is 0.2 meters. So this radius here is, let's call that R1, that's 0.2 meters. And then this outer radius is 0.6 meters. They give us the moment of inertia of the pulley. So they tell us the moment of inertia of the pulley is equal to 46.0 kilograms meters squared. And they tell us that the pulling force, or the tension, is 2,150 newtons. Okay. So at this point, we need to figure out all of the things that might be involved in solving this problem. We have a couple of torques. We have some forces. So we want to write out each of those expressions. So one thing that we know is that there are two torques acting on this pulley. Let's just consider the pulley itself for now. There are two torques acting on the pulley. One is the force that's applied by the motor, the 2,150 newtons applied over this larger radius. The other torque is the force of gravity from the weight of the crate pulling over the inner radius. So we can write that expression down now. We can say that the net torque is equal to the force from the motor times that outer radius. Let's call that R2. And that's going to cause it to rotate in the counterclockwise direction. So let's go ahead and call that positive, counterclockwise. The other torque would cause it, the torque from the crate pulling down would cause it to rotate clockwise. So we'll call that negative. And that would be the weight from the crate, so I'll call that W. And, or actually, sorry, we need to amend that a bit. That is we're just going to call that the tension pulling down for now. So we'll call that tension. And the inner radius. And that's going to be equal to the moment of inertia times the angular acceleration of the pulley. Right? So there we're considering the pulley. In order to solve this problem, we're going to need to consider some linear relationships as well. If we look at the box has a couple of forces acting on it. And for linear kinematics, we know that the net force acting on the box is going to be equal to the mass of the box times its acceleration. And so the forces acting on the box, we have a force acting downward, and that is the weight on the box. And we have a force acting upwards, which is the tension from the rope. And let me just switch the signs here real fast because it'll be a little bit, you can do it the way I wrote it, but it'll be a little bit less confusing if we do that. So we're just going to leave. The reason I made that change is because we have counterclockwise as being positive. So a force down here pulling downward would be in the negative direction. So the weight needs to be negative, the tension should be positive. Alright, so we can solve for this tension force, which is the same tension that appeared in the first relationship. And we find that the tension is equal to mass times acceleration plus mass times gravity, which is the weight. And so we can solve that and say that it's mass times gravity plus the acceleration. The reason we needed to consider this is because if the force pulling on the pulley is sufficient to lift the box and to accelerate it, the tension force is not going to be equivalent to the weight of the box. The tension force will be a little bit more than the weight of the box because we're pulling it up faster than we need to. And we can see that from this relationship here. If the acceleration isn't zero, if it's some positive value because we're accelerating upwards, the tension is going to be larger than the weight of the box. So that's what that expression is telling us. At this point, we have a couple of unknowns. We can substitute the tension back into this equation. We know mass, we know gravity, we know the pulling force, we know the radiuses, we know the moment of inertia. So the only unknowns that we have right now are the angular acceleration and the linear acceleration. But we know that the linear acceleration is equal to the angular acceleration times r. We just need to pick the right r. So if we look, as long as the rope doesn't slip,